Okay. I know you need to be downloading 20 if you haven't downloaded it, okay? I know that you're still a little uncertain about the first derivative test. That's okay. Kind of where you're supposed to be. We're going to talk a little bit about concavity and the second derivative test today, which is going to seem a little blurry to you maybe to begin with, but I think as you get the two things together, they start making things make a little bit more sense. The only way you get better at this stuff is by practicing it quite a bit. So that's the reason I'm having you do 19 and 20 and turn them in. This slide is not on your 20 there, so I just want you to think about this picture. So this is kind of picking up at the end, or kind of doing some of what y'all have been doing. Many of you have been taking your sign line that you've gotten and then drawing, this is what I think the graph looks like. And that's great. That's kind of where we're going to wind up in a few weeks, being able to do that. But in your mind, or on your paper there in Notability, sketch out, or maybe somebody will volunteer to come up here and sketch what the graph looks like. Come on, Mr. Mack. Okay. Now, can you mark on there where -2, where 0, and where 2 is for?
This is -2.
Okay.
I guess this is 0.
Okay. All right. Y'all agree with that? Okay. All right. And yeah, that's a pretty good indication of what the graph could look like. Now, I want to ask you a question. Where did we get -2, 0, and 2 from? They are the x's, and we call those what? Critical points. How do we find critical points? Derivative equals 0. Or undefined. Right? So its derivative is 0 or undefined. Okay? I'm going to give you another piece of information here. And I want to see if it changes what you think the graph should look like. Okay? At this point, f prime is 0. At this point, f prime is undefined. And at this point, f prime is undefined. Now, look at her graph that she drew in red. Does the graph match the information that I've got written in blue and green? No. The undefined part changes things? All right, so we agree that the red graph would match the blue, okay. But if we put the blue and the green together, the graph doesn't look like that. What does it look like then? Now, it's still got to, I'm looking for somebody that wants to draw a graph that looks like the blue and the green. Connor, are you volunteering? Or are you asking a question? Yes.
Could there be a hole?
Yeah. It could be discontinuous. The function could be discontinuous. So does that give you an idea of what it ought to look like then? Well, come on. Come share. I mean, there's only 14 of us in here. Mr. Mix won't laugh at you. So the rest, I mean, at most 13 people will laugh at you. Mm-hmm. I got you. I'm with you there, man. Okay. 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 Yes, sir? Sure. All right, let's look at, draw your pieces back in there, or I'll draw them back in there. Okay? You had something that looks like this. That was intriguing. Now, the question I want to ask you, does his black glass meet all the requirements of the blue and the green? Is the derivative negative over here? Yeah. Is the derivative negative here? Yeah. Is the derivative positive? Is the derivative positive? The derivative is undefined at these 2 points, isn't it? Because there's a jump. Okay. Somebody else wanted to come draw? Yeah. Question? Go for it. Come on. Come on. Let's see what else could happen. Okay. Does his graph meet all the criteria? Is it at the bottom? This part right here is what you're saying. The derivative has to equal 0. Right there. So how would you fix that? All right. So it's got to match up there. Okay. Does it meet now? Okay. All right. I want to draw a graph up here for you. Let's see. And here's what this graph's going to look like. Here's -2 over here. Here's 2, and here's 0. And let's see, we're going to have a function that does this, and then something that now, does that purple graph there, does it meet all the criteria? Is the derivative negative here? It's undefined. Is the derivative negative here? And then it becomes... Okay, now, all right. And now's where we start getting confused here. All right, these numbers say the derivative is 0 at those places, not the function. Okay? The derivative is 0. So the derivative is 0 here, but the function value could be anywhere through there, okay? Think of it this way. Let's go back to something real simple, a parabola. That's right there. The vertex is right there. The derivative is 0 right there. Would you agree? But is the function value 0? Because it's above. If I draw it up here, still the derivative is 0 right there, but the function value is not. And that's very confusing, okay? I can see some of you just got glazed over right as soon as I said that. Yes, sir?
But for the numbers you changed to undefined to that, they have no area where it's like that, right?
But what's the derivative right here? The derivative is undefined here too, because this function, I don't have a derivative here. It's getting more straight up and down. So it's possible for the graph to look like that. Well, how do we determine then, from our information, which one of these it looks like? And in order to do that, we talk about something called concavity. All right? Now, how many of you have heard of convex and so write a new definition using what you think should be the definition. Looking at that pretty graph there, where is this graph concave? And where? You were about to say something? She says it's concave from pi to 2 pi, convex from 0 to pi. Does that make sense to everybody? Convex means that it's up in the air. Okay? Here's the way I think of it. Concave will hold water. Oh, let's see if we can write that. Okay? They will hold water. If something is concave, it will hold water. If it's something is convex, it will not hold water. Okay? So you can look at that and kind of tell, all right? Now, every point on this graph, all of these points have concavity. That's what we're about to define. What do we mean by concavity? Well, if it's a concave, it's caved in, it will hold water. It's easy to see concavity with a group of points, but it's hard to see concavity when we're talking about just one point. One point, not points. Okay, one point. Concavity has to do with the second derivative. Okay? So, the second derivative. So, if we want to find, now all these words scare you, okay? Don't worry about it. You might want to actually read them sometime, but don't worry about them, okay? If the second derivative is positive, then it's concave upwards. Okay? If the second derivative is positive, it's concave upwards. If the second derivative is negative, it's concave downward. Okay? Well, what case did we not take into account there?
Zero.
All right. Okay, and I introduced a new word. Concave upward is the same as convex. No, yes. Yes. Concave upward is the same as convex, okay? So, what case did we not take into place there? What's happening at 0? Okay? So, what happens if f double prime equals 0? Well, what happens if f double prime equals 0? F double prime being 0 gives us a special new name, inflection point. Okay? Now, an inflection point is very similar to a critical point. What's a critical point? First derivative is 0 or undefined. Okay? That's a critical point. All right? Inflection point. Read this definition for inflection point. Tell me what's different. Second derivative is 0. So we're dealing with second derivative. Second derivative is 0. Second derivative is undefined. The minuscule other part that you're going to miss. Concavity changes. Convex is a word that I shouldn't have introduced, okay? Convex is the same as concave downward, yeah. Oh, I wrote this wrong. Yep. This is convex. Yeah. Concave means it's caved in.
Is that why they're called? Is that why they're called convection?
Yeah, you were right.
Concave upward is this.
How about concave upward? Not normal concave. Concave upward, what
No, concave down. The concavity is facing down.
Yeah. Note to self, change these notes, okay? Concave upward, it will hold water. It's pointed up. That's a good way to think. Concave up would mean just point it up, okay? Concave up means just point it up. Concave down means just point it down. The ends are pointed down, okay? Concave up will hold water. Concave down will not hold water. Okay? Critical thing to know here, though. The concavity has to change for it to be an inflection point. You don't know it's an inflection point until you know that the concavity changes. All right, now we'll worry about these other three things here in just a second, all right? But I want us to jump into a problem here right now. Okay, so let's look at this problem. Determine the open interval on which the graph is concave up or concave down. We're going to talk about that here in just a second, okay? You're ahead of us there. So tell me what we've got to do.
Find the first derivative.
Find the first derivative. And then what have we got to do? Find the second derivative, okay? I'm going to see this as that. So I'm going to say f prime is negative 8 x squared plus 2 to the negative 2 times 2x negative 16x over x squared. That's what I got, something like that. That's my first derivative. Okay? Will that allow me to answer the question? No. Good. Y'all on top of things. So now we need to find the second derivative. First, negative 16x times the derivative of the second. Negative 2 times the quantity to the negative third times 2x plus second. Yes, but it's going to be product rule though this time. It has to be. Because 16x, yeah, I got a negative 16x in there. So I've got to do product rule on it. Now, free advice, you need to factor that second derivative.
So wait, are we doing the same exact thing we've been doing, except for just saying whether it's doing that or that?
And at the end game, we're going to decide that. Okay? I don't want us to try to simplify too much just yet, but in the end game, we're going to be there, okay? Now, to the negative 2 or negative 3? Negative 2. Negative 3. We want to take out the smallest one, negative 3. So we're going to take out an x squared plus 2 to the negative 3. I want to take out more than that. Take out a negative 16 also. That'll just keep my numbers smaller, okay? So when I take negative 16 x squared plus 2 to the negative 3 out of this first thing here, I get a negative x. Oh, you're right. Just get an x, and then negative 4x. I'm going to put these things together to the negative 4x, and that's it. I'm factoring out x squared plus 2 to the negative 3, and I'm factoring negative 16 out. Yes, I misspoke there when I closed that. All of that's coming out of the first term. Plus, what comes out of the second term? X squared plus 2. All right? So now let's see what happens here. We've still got the negative 16. We've still got the x squared plus 2. We've still got the negative 3. Negative 4x squared plus x squared plus 2. Or even negative 3, I think. Negative 3x squared plus 2. Negative 16. And I'm going to move this thing to the bottom now. That's what I get for my second derivative. We're ready to start the problem now. because it was we took out to the negative 3, right? So it'll be, when I move it down, that negative 3 becomes a positive 3. Oh, it shouldn't be cubed, should it? Geez, I'm not very good with this stuff. All right, negative 3x squared. Okay, so now, go back to the question. Determine the open intervals on which the graph is concave up or concave down. What do you think we need to do? Set it equal to 0. When does this thing equal 0? When the top equals 0, okay? Can negative 16 ever be equal to 0? So we're not going to worry about that. We're going to deal with this. Negative 3x squared plus 2 equals 0. Ooh. Negative 3x squared equals negative 2. X squared equals 2/3. Plus or minus. Ooh, we got to square root that stuff now. Plus or minus the square root of 2/3. That's an ugly number. That's okay. Can't be. Well, I brought this over and it'll be negative, right? And I had a negative, so I don't think there's going to be a negative in there. If it is, then we're finished because it can't happen.
All that work for nothing.
Okay, so we've got, are these inflection points?
They're critical points.
Why are they not inflection points? We don't know if the concavity changes. These are possible inflection points. All right, go back.
Now if it goes to the left and the right,
Whatever makes the bottom 0. Look at this bottom. Don't do any work and tell me what the answer is. What makes the bottom 0? Nothing.
we can do this.
Does everybody agree that nothing makes the bottom 0? If I square it, it's going to be 0 or positive, right? And when I add 2 to it, it's got to be positive. So nothing makes the bottom 0. So now we need to, so we've got 2 still possible inflection points. So we're going to draw our second derivative. Inflection points are where the concavity changes, where it goes from being like this to being like this. See, look at, yeah. Do you see? Yeah. We don't know that they are yet, but we're about to find out. So we've got the square root of 2/3 and the negative square root of 2/3. Now let's write all of our factors. Don't forget to name this. Remember I told you we might have to do multiple sign lines in the same problem? That's why we need to name it. So our factors are negative 16, negative 3x squared plus 2, and x squared plus 2 cubed. Do you understand why I'm writing those 3 out there? Why am I writing? And those are all things that multiply and divide to give me my derivative, okay? Anything that's a factor, anything that multiplies and divides to get my derivative, I put out there. So I'm going to, I put negative 16 right there. Now, so if I pick a number smaller than negative square root of 2/3, what number that would be? Negative 1. Is negative 16 positive or negative? Negative. And if I put negative 1 in there, what am I going to get? It's one of them, I agree with you. Negative 1 squared is 1. 1 times negative 3 is negative 3, and negative 3 plus 2 is negative. What about the top one? What did we say about x squared plus 2? It's always positive. Pick a number in here. What's between negative root 2/3 and positive root 2/3? 0. Is negative 16 positive or negative? Negative. What about this one? What about the top one? What's bigger than root 2/3? 1. Is negative 16 positive or negative? What about up here? 1. Yeah. 1 squared is 1 times negative 3 is negative 3. Negative 3 plus 2, negative. What about the top one? X squared plus 2 cubed. Now, is the whole derivative, what's the sign of the whole derivative for this area below negative root 2/3? Positive. Because negative times positive makes it positive. What about for the middle ground between those two? Negative. What about in here? Positive. Yeah. Now,
Like, so the way I do that, I don't do it like that. I just plug in the number
to this, you're going to get the same thing.
Okay.
Yeah, if you're plugging the number in up here, you're going to get the same thing. Okay. Here's the reason. Katie, don't get comfortable doing this on your calculator, because that's the scary thing, getting dependent on your calculator. This is not a calculator problem. Now, so tell me, are these inflection points?
Yeah, they're possible.
Well, now we know either they are. Why are they?
It proves it. Because the math says so.
Because it was. What does it mean over here? The fact that it's positive. What does that look like?
Yeah.
It's
concave downward.
positive. No, positive.
If it starts up and then goes down.
Positive is concave upward. Okay? So what does that mean? Concave upward. That means here, in this area, it's going to look like this. Okay? What's it going to look like there? Concave downward.
So this is just looking at
The shape of it, yes. What does this look like? Concave upward, okay? So it gives you something to do with the shape of the graph. You don't? It could look like that. It could just as much look like this here, because that's concave up. This could be, how else could it be concave? Probably not. We'll get into drawing the whole thing here not very long from now, okay? That's right. So any of those things could be going on with the graph there, okay? But we know it's one of these two. It's one of these. It's one of these. It's something to do with concavity on those intervals. So as Sam said, it's just the same thing, except our answers now, our sign line is talking to us about concavity. Is it concave up or concave down? That's all we're talking about differently. Yes, sir? This is going to show us how to find the maximum and the minimum here very shortly. Okay? So, hold on before we go. All right, here's what I want to know. I want us to jump over to this problem, and I want us to work through, this will be the last one we work through today, but I want us to work through all this together, okay? Now, I'm going to change the directions, okay? First thing, find all critical points. Determine increasing and decreasing. Okay? What does that mean? Tell me how you're going to do 1 and 2. Which is? First derivative set it equals 0. Okay? First derivative, second derivative, sign line. Excuse me. First derivative, sign line is all you're going to do there. Step 3. Find all inflection points. Determine concavity. Okay? I want you to do those. You do those 4 things, you'll be at a pretty good spot there. This is a relatively easy problem to do all this with, though. Just leave it like that. Yeah. Okay? That's what I want. All right, so now let's do our sign line for that. 3 critical points. Yes, sir? What do you mean? No, I'm doing what I said to do in green first. I'm finding out there probably won't even be 3. Find all critical points. And determining this first 2 things that I'm asking you to do is what we were doing before we came into class today. Because we're going to put these 2 pieces together and see what they tell us, okay? Inflection points. All right, so look, I'm doing my critical points down here. This is all first derivative. I've got x squared, and I've got 5x squared minus 12. Well, x squared is always positive, isn't it? All right, and then what if I take a number smaller than that? Smaller than that would be negative 10. Negative 10 squared is 105. That's going to be a positive number. So I've got that the derivative, that the function is increasing till we get to 12/5. What happens between here? That looks like a 1. 5 minus 12 is negative. So the function... Okay, I'm putting 1 right here. 1 squared is 5. 1 squared is 1 times 5 is 5. 5 minus 12 is a negative number. You agree with me? And when I put negative 1 in here and squared, I'm going to get a positive. So this is going to be a negative number times a positive number, and a negative times a positive gives me a negative number. Now you're doing the same thing up here though, right? You're saying negative 1 squared is 5 minus 12, right? So you're getting a negative number. You're just getting the negative number. I know that it is a negative number. Yes, sir. This here I use negative 10. This is 2 something, right? Square root of 2's got to be less than 2, so I use something bigger, something further down through there than that. Negative 5, negative 10, something like that. What happens when we put 1 in here? 1 squared, positive. 1 squared is 5 minus 12. It's going to be negative. So it's negative. Okay? What about when we put something bigger than 12/5 in there? Like the 10. I think we'll find out that it's positive. So we found out that the function's going down to 12/5. Then it's going up to 12/5. Then from 12/5 to 0, it's going down. At 0, it's 0. After 0, it goes down again. And at 12/5, after 12/5, it starts going up. So the function, we've got some idea of what's going on with the function here. Let's now look at second derivative. Yes. Where is this saying decreasing in? It's decreasing on those intervals, and it's increasing on these intervals. Yes, all of those should be 12s over 5. You can read it a lot better if I write over it 3 or 4 times, can't you? I mean, that's what I always do. Don't know why I do that, but that's what I do. So our second derivative is going to be 20x cubed minus 24x. And what can we factor out of that? And we get 5x minus 6 equals 0. So x is 0 and x is 6/5. Oh, it should be, yeah, 5x squared. So all of that I messed up on there. So x is plus or minus the square root of 6/5. I can. Are these inflection points? We don't know. Why don't we know? We've got to do a sign line. These are possible inflection points. And I keep saying that because tomorrow when you're working on this, you're not going to think they're inflection points. Okay? Maybe we'll find out right here. That's right. Yeah, that's right. Exactly. If this were our sign, 0 would. That's right. Exactly right. Wherever the signs change. 0. Square root of 6/5. Negative square root of 6/5. All right, now I've got 4x and I've got 5x squared minus 6. Well, 4x is going to be negative and it's going to be positive in those areas there. Does everybody see how I know that? Because if I put a number less than 0 in there, it's going to be negative. So boom, boom, it's got to be negative. If I put a number greater than 0 in there, it's got to be positive. What's a number? Well, what's a number out here left of negative 10? Negative 10 squared is a positive 100. 500 minus 6 makes that positive. So then the whole derivative is what? Negative out there. What's the number between 0 and the square root of negative square root? Negative 1. Negative 1 squared is 1. 5 times 1 is 1. 5. 5 minus 6 is negative. And negative times negative is positive. Then we'll put 1 in there again. I bet we'll get the same thing out. It's going to be negative, yep. What's bigger than root 6 over 5? 10. A million. Just anything that you know is bigger than that. 10 is. 10 squared is 100. 500 minus 6 is going to be positive. So it's going to be positive. Is that really our sign line? Third one's, oh yeah, it is, isn't it? It is. I wrote positive. I was thinking negative, but okay. So yes, all of these are inflection points. All right, those are inflection points. Does this help us to know where maximums and minimums are, though? Okay. Well, let me ask you something. Where is 12/5 at on this number line down here? Where's the square root of 12/5? It's on one of these sides. Agreed? Which one is it? Think it's over here? Okay. All right, so I want you to tell me, take into account what you know. Up here, 12/5 make the first derivative 0. The square root of 12/5 make the first derivative 0, right? So that means it's either a max or a min, right? That means the derivative looks like this. Agreed? Well, what does the fact that it's over here says that the second derivative is positive. What does the second derivative being positive look like? Looks like this. So we know the derivative looks like this, and the second derivative tells us it's concave up. Therefore, this point is suddenly a minimum. Okay? So we can take the second derivative and the first derivative and put them together and say, hey, that's a minimum there. Let's look over here at negative 12/5 now. Negative square root of 12/5. Okay? First derivative says it's 0. Second derivative is negative, right? Well, what does the second derivative of negative mean? Just concave down. That means it looks like that. So what's that point? Max. Wow! Could you have told that from the other sign line? Yes, you could have. Okay? This is another method of checking behind, I guess is the best way to think of it there, okay? Yeah, you could, but then it gets really messy. I would never mesh the two things together. So, what I want you to come away from is what would it look like? That's a very good question. So let's see. We know, all right, some of y'all read off what we know. We know that there's a max at root 12 fifths, right? Root 12 fifths, we know there's a max. So it's got to look something like that around it. All right? Tell me. Oh, it's a min. Okay, thank you. It's a min. Okay, so we know it has to look something like this. Come on, give me my purple back. We don't know where it is, and I'm purposely drawing it up there to confuse you here, okay? We know that's a min. What do we know about negative 12 fifths? It's a max, okay? I'm fixing to blow your minds, okay? There's the max, there's the min. They're relative max and relative min, okay? So, now, what else do we know then? At 0, what do we know? The derivative is 0 and the concavity changes. So, somewhere in here, it does this, doesn't it? It has to do something like this. Was that right? Which way was it concave up? No, it's concave. Is this concave up, people? No. It's not concave up. So it's got to be concave up. It's got to be concave up like, whoops. What does this say? It has to be what? Concave up. So it's got to be concave up like this, and it's got to be concave down like this. That's what it's got to look like around here. It is. It's decreasing, but it's concave up.
But it makes sense because on the original sign there, like there's negative right there.
So now, what else has to happen? We know it's going to look like this, and we know that it's going to do like this here. So actually, we can actually know now that this point can't be there. It's got to be down here somewhere. And this point can't be. It's got to be. So suddenly, by doing a little bit of thought process, we figured out that this function has to look something like this. Now,
If we had drawn that from the first time,
we don't know that. Oh, yes. But now, here's something I want you to understand. This graph could be shifted up the page 500 points. It could be stretched out. This point that we've got drawn right here could actually be somewhere way down here. This point could be way down here. We don't know where, but we know that's the general shape of the graph, okay? That's enough. All right, you've glazed over, so let's talk about what you need to do, okay? After your turn is what I want you to be looking at, okay? Determine the open intervals on which is concave up or concave down. What do you do?
Same thing we just did.
Second derivative, set it equal to 0, concavity.
Can you just do, like, on the last one, what you've been doing?
Yes. I only want you to follow the instructions here, okay? Follow the instructions as they're given. Concavity, second derivative, set it equal to 0, and do concavity.
What is number 1 actually?
Good question.
There's no equation.
Yeah. State the signs of f prime and f double prime. Is the first derivative of this, first of all, Is the function increasing or decreasing? See, she says increasing. All right? F is increasing. What does that tell you about the derivative? F prime is greater than 0. All right, is it concave up or down? Okay, it's concave up. So is the second derivative positive or negative? Positive. You need to go back and look at your words there, okay? That's all we're asking you to do, Connie. Look at the graph. Is the graph increasing or decreasing? If it's increasing, it's concave up. If it's increasing, the first derivative is up, greater than 0. If it's decreasing, the first derivative is less than 0.
But on the next one, can it be increasing but be concave down?
Can it be increasing and concave down?
Yeah. Okay.
Look at this here. Isn't the function going up? But it's concave down. It won't hold water. So yeah, it can be that. So I want you to follow the instructions on those problems and solve those problems, okay? They need to be turned in tomorrow night, no later than tomorrow night at 10:30, okay? Sorry this took longer than I anticipated, all right? This is the last thing we're going to learn before our test next Friday, okay? The last thing we're going to learn. However, we're going to spend some time Monday and Tuesday and Wednesday trying to go through and review some things and get you to do a video problems, 2 or 3 video problems, and maybe a web assignment. There's some different things to get this under your belt because this is big ticket what we're talking about.